Hi, my name is Lucas Sanchez, and today we're discussing a system that we know to be adiabatic, and we have some flow of inlet into the system, and the inlet flow and the reactants cause a combustion reaction, and which forms a flame in the adiabatic system. And we want to figure out how we can calculate the temperature of this flame. And to do that, the key is going to be relating enthalpy into the temperature. So we'll start off by deriving an equation that relates enthalpy to temperature. And our first starting off point will be the internal energy of a system. So as we know from earlier videos in this class, we have found that the internal energy of a system, or sorry, I should say the differential amount of internal energy of the system, can be expressed using this equation here. So we can say differential amount of internal energy, which can be expressed as the enthalpy plus the kinetic energy plus the potential energy is equal to the, again, the same things, enthalpy plus the kinetic energy plus the potential energy times the differential amount of mass coming in minus the same things, enthalpy plus kinetic energy plus potential energy times the differential amount of mass coming out of the system. And then we'll also have plus the non-flow work and the heat of the system, or different amount of heat in the system. And we're going to draw the system out to get an idea of what it's going to be looking like. So we have some input coming here, we'll call it I, and some output coming out here. And then here we'll have the flame, and we don't know what the temperature is. So our system here will be known to be at steady state. So this term here will be 0. We're not going to do any extra non-flow work to the system, so this term will cancel out. And we're not doing any heat to the system, or taking away heat from the system. So that's going to be, because it's adiabatic, so heat's not being added or removed from the system, so that's going to be 0. The kinetic energy of the inlet and the outlet will be similar, so negligible will be, oh, sorry, this is 0 already, so this can be 0, this can be 0, and as you can see, there's no change in height, so there's no change in potential energy. So I think our equation very simple. We'll get 0 is equal to H in minus H out. And the same amount of mass is entering the system as the same amount of mass is leaving the system. So the dm and the two terms cancel out.
Hey,
Hi, how are you?
I'm there to check the TV. I usually come in here, but you're fine.
Okay, perfect. Thank you. You too. Sorry for the interruption there. So the Hn enthalpy of the inlet will be the same as enthalpy at the outlet here. And like we said, we want to express enthalpy as a function of temperature. So we'll go ahead and say, we'll use CO2 for example. So the enthalpy of CO2 will be equal to the enthalpy of CO2 at some standard temperature. We'll say it's 298 degrees Kelvin. And that's going to be plus the specific heat of CO2 times dT. So in order to calculate the enthalpy at a certain temperature, related with temperature, we'll have to integrate this term here. And we're going to look at HCO2 Kelvin plus the integral of Cp to be at 298 degrees Kelvin, some different temperature, dt. And we ourselves are not going to integrate that. We're going to use Wolfram alpha because this relates to equation 107 in ChemCAD. So let's head over to Wolfram alpha to integrate this expression here. Here is the equation 107 that we'll be looking at. It is for the heat capacity of a certain substance, and it's dependent on temperature here. These A, B, C, D, and E constants will all be provided to us, and they're given to our disposal in that library. So all we have to do is integrate these C and E terms, and then again plug them into the original function that we have for enthalpy, and then we'll go ahead and move forward using Python to figure out what we need to know to solve for the temperature of the adiabatic flame. So we'll go ahead and we'll integrate the first term. It's going to be C divided by T. Gosh, I can't type today. Divided by hyperbolic sine of C divided by T, and this is all going to be squared. So to the power of 2, and then we want this dependent on temperature, so we'll let them know that. And we're going to integrate it. So we get that for the C term. And then we'll go ahead and integrate the other function. Open the from alpha again. So we're going to copy and paste this because they're really similar terms there. So we'll change C to E, sine to cos, and E to C, or C to E, I should say. And we go ahead and integrate it again. And we get that. So let's go ahead and fix up our final integrals here on our board so we can get our expression that we want to solve for. So obviously we still have enthalpy of CO2 plus the integral of CPdV, but we just calculated this integral to be we just calculate this integral to be, let me switch this 1 second. It will be plus A T, and these constants will all be defined for us, plus B times, what was the first integral? B times C times 1 over sinh of C over T to the power, oh no, plus D times, or no, minus D times E 1 over, no, E times, this is not sinh, this is tangent, 1 over tan. And this will be E times tangent, hyperbolic tangent of E over T. So this will be our expression that relates enthalpy and temperature. So now we have the expression, we can go ahead and take it over to Python to solve for the rest. Before we start coding it, I wanted to get some backstory, or not backstory, what should I say? Before we start coding it, I just want to give some knowledge on the problem we're trying to solve here. So the inlet here has some inlet of natural gas, and that is composed of 95% methane, 4%, what the fuck was it? So before we start solving the problem on Python here, I just want to get some context on the problem we're solving. So we have an inlet of natural gas here, and the natural gas composition is 95% methane, 4% ethane, and percent N propane. And obviously, they're going to react in a combustion reaction to form H2O and carbon dioxide. During this reaction also, it's going to have excess air, 200% excess air in the reaction, and this can all completely combust. It's going to be 100% combustion. So on this side, we're also going to have additionally we're going to have nitrogen and oxygen here, and the same, we'll have more oxygen on this side and more nitrogen, so we'll have excess air. So now we know I have some back knowledge on the problem. Let's get started by solving it. All right, so we're going to start off by coding this. I've imported the template in the GitHub site to use the props that we need to solve this problem. So we'll start off now by importing numpy smp, and we're going to need the root solver. So from scipy.optimize, we're going to import root. And then we need to pull our compounds or our substances from the props. So we'll call it P, and that will equal props. And the first thing we need is methane. And then we'll need ethane. Make sure everything's spelled right. We'll need N propane. We will need oxygen. We will need carbon dioxide. We're going to need water, and we're going to need water, and we're going to need nitrogen. So make sure you spell everything right. Check's perfect. Now we'll define our fuel comp. So our fuel comp was going to be np.array. We had 95% or 90% ethane or methane, 0.04% of or 4% of ethane, and 0.01 of propane there. And then we're going to create a matrix that will allow us to calculate the actual number of moles of each of our reactants here. And by doing a matrix multiplication with this matrix and the fuel comp, we'll actually be able to figure out the number of moles of carbon and the number of moles of hydrogen that we'll have in the reactants. And from there, we can solve for the other compounds in the reaction here. So we'll say the matrix will be equal to np.array. It will be equal to, so the first one is we're going to use the number of carbons in each of the reactants. So in the first methane, we just have 1, and the second we have 2, and the third we have 3. And then the next array will have the hydrogen, so we'll have 4, 6, and 8. All right, so we'll use a matrix multiplication, and we'll see what we get for the number of moles of carbon. Perfect, so we'll have 1.01 moles of carbon and 3.92 moles of hydrogen. Equals fuel comp there. So from the reaction, we know that the total number of carbon will be equal to the number of carbon dioxide moles And we also know that the total number of hydrogen atoms will be equal to half the number of H2O molecules. NH equal to NH2O. We did it the wrong way. We know that we also did this wrong too. CO2 equals NC divided by 2. The total number of oxygen molecules will be equal to the number of carbon dioxide molecules plus the number of hydrogen water molecules divided by 2. So we'll say NCO2 plus NH2O divided by 2 will give us the number of oxygen molecules. But we have to remember that oxygen is in excess in this situation because of the excess air. So the number of moles of oxygen in the stoichiometric balance will be this number, but will be in excess too. So NO2 will be equal to, we'll have to define that amount of excess air, we'll call it E air, will be 2, will be NO2 underscore stoic times E air plus 1. And then the amount of nitrogen in this situation, N2, will be equal to this amount of oxygen, the NO2, times that ratio of 79 divided by 21. Times. All right, so now that we have this defined, we'll want to create our moles in, an array for the number of moles in and an array for the number of moles out here. So in order to create a number of moles in, we'll concatenate the field comp array into the new array we want to create. So NP, say moles underscore N will be equal to NP dot concatenate, and we'll have to input a list of fuel comp. The next array will be NP dot array, and we're going to have to input, so oxygen, we start with the stoichiometric amount of oxygen. We'll have no carbon dioxide, no water, and nitrogen will be just N2 here. And then we'll create another array for the number of moles that are coming out of the system. And since we know that the reactants are completely used because it's 100% combustion, we'll have 0 of each of those. And then in terms of oxygen, we will have just the excess amount of oxygen. So it will be NO2 underscore stoic times E air. Carbon dioxide will have NCO2. Water will have NH2O, because those are what's forming in the system here. And then nitrogen will stay the same because it's not involved in the reaction at all. It's just there because the excess air is there. Shift enter. What did we do wrong here? Forget to include brackets. Perfect. All right, there's an array there. And now we can start by solving this problem. So what we need to do is define our equations that we derived earlier in the video, in earlier parts of the video, and we'll start off by defining the what was it called? The integral of the heat capacity depending on temperature there. So it was quite the long equation, but it was P dot, we'll have to import the props. Like I said, the constants here are going to be the heat capacity constants that we saw in the equation, but they're in this library stored here already, so, or this notebook here. So we'll be able to import those to help them solve the problem here. So IGA will be the first one, times T. I'm missing the return statement here. A times T plus, it was P dot CP IGB times, was it C? No, times P dot CP IGC times, or divided by tangent NP dot tan H of P dot C CP IGC divided by T. Parentheses just for safekeeping, and then we subtracted from that D P dot IGD times this whole similar function here. It was P dot IGE times tan NP dot tan H of P dot IGE divided by T. So there's our first function, and then, like we said, we use this integral of Cp, depending on temperature, in the final expression for enthalpy. So enthalpy, depending on temperature here, was equal to H of 298 minus H of T minus, H of 298 minus, why am I freezing here? Shoot. 1 second, I'm freezing, completely freezing here. All right, we actually had quite a few errors in the code here. First of all, we had this initially as NC, or number of moles of carbon dioxide was the number of moles of carbon divided by 2, but that's not true. The number of carbon dioxide in the system here is equal to the number of moles of carbon, so that should not be divided by 2. The other error we had here is we figured out that net collect that the heat capacity for the constants here were defined in terms of mole or joules per kilomole here. So we had to divide by 1,000 here to get them in terms of moles. And then one final thing is we flipped here the integral of the heat capacity here. It should be T minus 298, not 298 minus T. So now we made those solutions here, we get a final value of around 1,355 kelvins of the temperature of the flame here.